Okay, so in this video, we're going to look at a few more examples of finding area between two curves. And the very first one we're going to look at, this example 3, is going to actually illustrate the fact that we don't even have to measure things top to bottom in what we would consider more of like a function, like orientation, right? Because we'd have y in terms of x. You can also do x in terms of y. As long as you represent everything within that particular variable. So, and that's exactly what this is going to look at, because the problem becomes if I try to measure top to bottom in this situation, it works for a little bit, right? I can go top to bottom here, and that distance is fine. It's bound between two curves, and that distance is bound between two curves, and that distance up to a point. But then all of a sudden, here, like those, that distance right there, the top, like I'm taking a function or a curve and subtracting itself, and so it's going to net you 0, even though that does represent area. So you have to always be bound between two separate curves, and I use the word curve intentionally because it doesn't necessarily have to be a function. Because if I think about drawing curves or drawing measurements between the curves in this direction, so every time, like if I think about these rectangles going in this orientation, like starting there, instead of going top minus bottom, think about going right minus left. You're always going to be bound between two separate curves. And so we're going to have to kind of think about, okay, measuring things instead of top minus bottom, which would have been highest minus lowest. We'll kind of keep that same analogy, but then quote unquote, the highest is on the right? The biggest is on the right. So it's going to be right minus left. And then we always started on the lower x value. So in this case, we'll start at the lowest y value, which is down here. So kind of like stack up, like I always think of pancakes, but it's breakfast time, at least right now. So I'm stacking these up, lowest to highest. So I want to know this point of intersection down here is -1, -2. Oops, sorry. Get the pen there. So it's -1, -2. And this y intersection up here is 1, 2, 3, 4, 5. And then 1, 2, 3, 4. So 5, 4. So since I'm stacking them and I'm using their y values, though it's the y coordinate that's going to become my bound. And so then in the right one is the linear one and the left one is a quadratic. And it's already x in terms of y, which is perfect. So I need everything in terms of y. So now my integral expression will be from -2 to 4 of the right curve minus the left curve. So I just wrote that now. And again, and it's going to be in terms of y. When you're measuring things horizontally in that direction, it's going to be in terms of y. So the right curve, we said, was y plus 1. I'm sorry, -2 to 4 of quantity y plus 1 minus quantity 1/2 y squared minus 3 dy. And again, this whole quantity is the right curve, and this whole quantity is the left curve. And that's all we have to do. We just have to set it up. Now, you could simplify that or just leave it like that. That's fine. But the key is that that you have written them in terms of y, your bounds, the curves, and also your derivative dy. Okay. Next one. Let K be the region bounded. I think I've used both words by the curves of sine x and cosine x, x equals 0 and x equals pi over 2, right? But do not solve what would represent K. So we have to have a little bit of knowledge about our sine function and our cosine function. Remember, sine function starts at 0, 0 and does this very nice and aesthetically pleasing balanced curve, right? So the thing is that like here's 0, here's pi over 2. So we're not going very far. Cosine, remember, cosine starts up here at 1, and it's going to hit, right? It's going to hit at pi over 2 down there, Okay, so again, it's not very far into the graph. X equals 0, which is a vertical line, and x equals pi over 2, which is a vertical line. So all of the space that would be bound with those would actually be these two symmetrical, almost triangular shapes. And the point of this example is to illustrate that when we can measure these top to bottom, no problem, because like going top to bottom, I'll always be in between the two curves. Like the x equals 0 and x equals pi over 2 sort of serve as my boundaries. And if I can measure from top to bottom, right, I'm always bound between two curves. But the thing is that what is on top and what is on bottom switches. So up until this halfway point where sine and cosine equal each other, which is by symmetry, it's pi over 4, right? 45 degrees, their sines and cosines are the same. Right? So the top curve, when I first start, is actually cosine. So when I set up my integral here, to write out this area, so k could be represented by from 0. First, I got to go halfway, so just a pi over 4. Top function would be sine of x. Cosine of x minus the bottom function sine of x. So that will give me the first half of that. But then, as soon as I hit pi over 4. I have to switch the order, pi over 4, up to pi over 2. Now, on this side, it's the sine function that's on top and the cosine's on the bottom. So sine of x minus cosine x dx. So that's one way to represent this. Now, just by symmetry, both areas are the same. So you could have also said, oh, well, k could be 2 times just one of these integrals. And it really doesn't matter which one, but I'll be honest, I would choose the first one because you get a 0. Anytime you have a 0 as a boundary, it makes it easy to evaluate, I think. Okay, so next example, it says, again, very similar, that the order of the curves is changing. So I'm noticing that like this region here, the top function would be the linear function, which looks like g of x. And the bottom function would be f of x. Okay. Now I'm going to do this a couple of different ways because sometimes if g of x and f of x is already defined, you can make it very efficient to represent your integral by just using g of x and f of x. So and again, by symmetry, I know that these regions are exactly the same. So I could say my area, I'll just call it A, is equal to 2 of, I'll start at 0, and then I can tell that that's 2, 0 to 2. And if you're not really sure if you're, is the scale right, you can try just putting in 2 because 2 cubed is 8, and 1/8 of 8 is 1, 1 plus 2 is 3, half of 2 is 1 plus 2 is 3. So I know that is 2, 3 right there. And this right here is 0, 2. So I'm going to go in terms of x, top minus bottom. So top minus bottom, and then in terms of x. And so then, and I'm doing 2 of them because I know by symmetry, they'll have the same area. So 0 to 2, the top function is g of x, and the bottom function is f of x dx. So, I mean, technically, that's one way to represent that area because I've already defined what f of x was and what g of x was, right? Now, if you wanted to write out what they were, that'd be fine too. Now, it says first write it in terms of x, which is great, which is what I did. Then it says write it in terms of y. And that's sort of an interesting problem. I kind of like this because if you think about, drawing, I guess we'll go maybe that blue, drawing top to bottom, right? You're always going to be bound in both regions, both this side and this side. You'll always be bound between two separate curves. But guess what? If you went right minus left, you also would have been bound between the two curves. At every instant, right? At every instant, if you were measuring horizontally right to left, you're still bound between two separate curves, and it's still right, still symmetry. So I might look at just this right side and do two of them, just like I did, in terms of x here. So my area could be two of my integrals, and I'm going to go right minus left, and I want to do things in terms of y. So that first means that my bounds, like the lowest one, if I'm thinking about like stacking these up, it's the lowest one is at 2, the highest one is at 3, in terms of the y coordinate. So lowest is 2, highest is 3. So at least I know my bounds here from 2 to 3, but now the right curve has to be in terms of y. The right curve is the cubic one. So if you think about, that was f of x, so we could say that y equals 1/8 x cubed plus 2. I need to solve for x in terms of y, so I subtract the 2. So y minus 2 equals 1/8 x cubed, multiply both sides by 8, so 8y minus 16 is equal to x cubed, and then I do the cube root. So the cube root of 8y minus 16 is equal to x. So that's my rightmost function. So my area is 2 integral from 2 to 3 of the quantity, and the cube root already makes it a nice grouping symbol, so I'm okay. 8y minus 16 minus, now the left function, or I should say the left curve, was 1/2 x plus 2, right? So over here, if it's y equals 1/2 x plus 2, so subtract the 2, so y minus 2 equals 1/2 x, and then double. So 2y minus 4 is equal to x. So that could represent the left curve. So then minus 2, the quantity, 2y minus 4. Now here it is important that we do write that in parentheses, because this is the right side of our rectangle, or our line measuring between the two curves, and this is our left. So I like that problem, and I think I mentioned this in the first video that sometimes on the AP exam, they're not in this application, they're not interested as much in can you now solve it, but more so, did you apply this idea of finding area bound between two curves, top to bottom or right to left. Now, also, I would say if they didn't tell us the instructions like to do it this way, then you could have a choice. And sometimes, and we're going to find when we start doing some volume problems, that sometimes in terms of one variable becomes a little bit easier than the other. Okay. And then our last one here, I think on this is just find this area. We'll just set it up, but everything's in terms of y, x in terms of y, x in terms of y. So I'm going to do this in terms of y. So I need to figure out when do these two intersect to start with. So I'm going to algebraically just set negative 2y plus 6 is equal to y squared minus 4y minus 2. So I'm anticipating 2, it's quadratic. One's a parabola, one's a line, so I should know that too. So y squared, let's see if I add the 2y over, so it's minus 2y, then subtract the 6, so it's minus 8. So 0 equals y minus 4, y plus 2. So then y is equal to negative 2 or 4. So at least I knew, right? I kind of knew that there'd be 2, one lower, one higher. So I know that when y is negative 2, and y is 4. Those are my 2 points of where the two curves intersect. Now, I don't know exactly where, but if I put y equals negative 2, I would get an x value of 10 in either one, right? Negative 2 times negative 2 is 4 plus 6 is 10. So when y is negative 2, x is 10. And then if I put in 4, negative 2 times 4 is negative 8. Negative 8 plus 6 is negative 2. So at 4, we're at negative 2. So this is negative 2 comma 4. So we're going from yeah, so for the lower y value, so I wrote that wrong. My apologies. I was like looking at that, I'm like, that looks funny. 10, -2. So again, we're going from a lower bound of -2. Oops, I thought I highlighted. A lower bound of -2 to an upper bound of 4. And so I need to figure out what's on the right and what's the left. And maybe you're not super familiar with how this parabola is graphed. And that's okay. And here's a nice little trick. So pick a value, pick a value that's sort of easy, and then compare the two. Like, for example, let's pick y equals 0. Like, what's happening at y equals 0? Because y equals 0 is on the x-axis. One's going to be farther right than the other. So in this one, when y is 0, the x value is 6. When this one, y is 0, the x value is -2. So at 0, the line is at 6, where the curve is at -2. So that sort of tells me that the parabola must be going in this direction, where the line is going in this direction. So that, again, picking that one data point to kind of help me figure out which one was farther to the right. Because now when I measure this, the right side to the left, I know which curve is on the right. It's the linear function. So then let's go ahead and just, again, set this up. Integral from -2 up to 4, the right function, I shouldn't say function, the right curve, being the -2y plus 6, the left curve being y squared minus 4y minus 2. And again, I'm okay for this example, just kind of saying, hey, we set it up, and I know we've already been tested. Can you solve antiderivatives? So this one is just more of that application. So a little bit of a maybe longer video, but I wanted to really emphasize. I thought I would get in for the bell. I really wanted to emphasize and kind of talk about a few of the concepts behind this. So hopefully this is good. And if you have any questions, come into the office hours and we can keep working on these examples.